Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. So this is lecture number 50 and tutorial 12. Now in the last lecture, that is tutorial 11 and lecture 49, we saw what the weight of any system was. The weight is the number of ways in which the different EIs and NIs could be reached, right? And for maximal stability, we wanted to ensure that all possible states could be accessed by the system, right? So in other words, we had to mathematically maximize W, right? And maximizing W was equivalent to maximizing ln W, okay? And this had to be maximized subject to the constraints. These are from the previous lectures themselves, subject to the constraints that the total number of molecules present is a constant and the total energy of the system is also a constant given by these two expressions right here, okay, right? So, and of course, we also saw that because we would be more conveniently dealing with ln W, using the Stirling's approximation, we had an expression for ln W derived. Okay, so in this tutorial, we shall continue from where we left. Now I'll just delete this part. We'll continue with where we left and we shall derive the expression from the Boltzmann distribution. So the task that we have is to minimize your maximize ln W subject to the constraints of the total number of molecules being constant and the total energy being constant given by the expressions that we just deleted, okay? So in other words, my d ln W, right? D ln W minus, well, because I have to maximize, right? So I'll just write down the expression for maximization. Minus alpha plus beta times sigma over I EI dni should be 0. Now what is this expression and suddenly where is this coming from? Well, I had to maximize ln W, right? Subject to the conditions that my dni, the sum of all the small the states, is going to be giving me the total number of molecules. The sum of all molecules present in each energy state is going to be giving me the total number of molecules, and the product of EI times dni is and when I sum over it over all the energy states, that is also going to be giving me the net energy. Okay, this is what I have to do, right? Now you may be wondering, where are these two random constants alpha and beta coming, right? I mean, I understand, okay, this is the maximizing the ln W part. Of course, when I maximize, using the calculus at turning points, right? I want this to be 0 overall, right? I should also be, dealing with the second derivative also, but I'm not going to be concerned. I'll just stop with the first derivative for now, okay? So now the this term, the dni term, I understand, and this EI dni term also I understand. But what about the prefactors alpha and beta, right? The question is, where are alpha and beta coming here? That's a fair question, right? I have to maximize this subject to this condition and this condition. But why should there be, the constants alpha and beta? Well, mathematically, there's a reason, the jargon for it is called as, these are called as undetermined multipliers, okay? But let's not go there, okay? Let's just limit ourselves to a discussion on physics and chemistry. See, the point is, look at this. What is the dimension of your dni in terms of n, right? In terms of molecules. Now, what is this dimension? It is in terms of, it's EI times dni, right? So it's in terms of energy, right? What about W? You get what I'm saying, right? So the different terms, there are three terms here in this equation. Term 1, term 2 and term 3. They all have different dimensions. So you can consider alpha and beta, right? beta, right, as added. I mean, we've included, okay, as being included to ensure. Let me call this equation. We are maximizing W, so I'm just going to call this MW. Okay, this is equation MW to ensure equation MW, right? Equation MW is dimensionally correct. Okay, so please be clear about this. The idea is that, we have to maximize LNW subject to the conditions that the sum of all the total number of molecules in the minor states is equal to the total number of molecules, and the net energy is also obtained as the energy of each of the molecules present in each of the state times the energy of that particular state. Okay, summing over all the energy states. Okay, right? So because we have like different different dimensions in each of these different terms, to make sure that we meaningfully add all of them, right, we include these terms alpha and beta. All right, are we clear about this? Okay, now having added this, okay, let us now notice that your d ln W, okay, this particular term d ln W, right, can also be written as now your d ln W, right, can also be written as this is what is called as a total derivative. Okay, right? Now the net change in your d ln W, right? Okay, your net change. What this tells you is that you bring this dni over here. Okay, right? So the net change of ln W with respect to your NIs is going to be given by the change of weight. See, the net weight is a constant. It comprises of all the NIs, right? It is going to be given by the sum of all the independent NIs. Did I make sense? I will explain this further. See, note that the DNIs are independent. In other words, let's say if there is a state E0 and it has like at any instant N0 molecules and E1 has N1 molecules, right? Please understand that now my N0 is not influenced by N1. N0 is an independent number. Of course, they will change, okay? They will keep changing with time, but these are independent. Now, because these are independent, right? The net change in dLnW, right, over dni, right, can be expressed as a sum of the LNW, right, with each of the NIs keeping the others constant, and that's why we have the dou symbol here, which is a partial derivative. Are we clear? So the basis for this expression is that each of the DNIs are independent. Okay. Now that we have this expression here, let's try to substitute it in MW, right? MW, and I will be going back to the other corner of the board for this. So I have this expression MW, and I'm going to use this particular linear approximation, right? This particular linear approximation, which is based on the idea that the DNIs are independent. I'm going to use it in equation MW to get the following: sigma over I. It's already here. Dou ln W by dou Ni times dni minus, one more thing. I mean, you can always ask me, okay, I understand that I'm having alpha and beta over here, but why a minus sign and a plus sign here? Well, there is no reason. I could have chosen this to be plus or minus alpha, but as you will see, it is for convenience that I've chosen this to be minus here and plus here. It is for mathematical simplicity. The reason will be more clearly evident as I finish the derivation. Okay, so I have this expression right here. I'll go back to the main point, and this is I'm substituting this expression dlnw in this expression mw. Okay, right? So I have written the first term. The second term is going to be here, minus alpha times sigma over I dni plus beta times sigma over I ei dni, and this overall has to be 0, right? Are we good? Now, do you understand what I've done here, right? I've simply, used the idea that each of the ni's are independent, okay, right? Because each of the ni's are independent, I can always write your the change of d, l, and w, right, as a function, as a change in the ni's instantaneously as the sum of the partial derivatives. Okay, right? So now that I have, by doing this, I get this expression. I'm going to call this expression as, so this I called as the modified version of W. This I'm going to be calling as the final version of W. I'm just going to call this as FW. I'll now delete this part. Now, look at the expression FW. Okay, I have the expression FW. Now, if I take a look at this, okay, I understand that throughout this, the DNIs, right? See, I have the sum of 3 terms. I have sum of 3 terms to be equal to 0. Okay, right? At any instant, my DNIs themselves are not 0. Because if the DNIs were to be 0, right, then I will be trivially getting that 0 equal to 0, right? I substitute DNI equals 0, right? DNI equals 0, I get like, oh, this is a multiplicative term. Sometimes something times 0 is going to be 0. Term 1 will be 0. Term 2 will also be 0. And term 3 will also be 0. Correct? So therefore, right, for DNI equals 0, right, I won't be getting any solution to this expression FW. Okay. Instead, what I therefore see is that because my DNIs cannot be 0, right, I see that the terms within the sigma, this particular things, my dou ln W by dou Ni, right, minus alpha plus beta EI plus beta EI should be 0 for all I. This is to solve this equation FW. This particular condition should be met. Correct? Okay, right? What am I talking about? This expression, right? My dou ln W by dou Ni, right, minus alpha plus beta I should be 0. Are we good? We're fine, right? Okay. So why is this valid? Because for each I, this should be 0. Now see, now the thing is, now we therefore should compute this particular expression, given that your LNW is this, okay? Your LNW is this. Your LNW is this. So you must now compute this expression. In fact, just hang with me. I told you that I've chosen alpha to be negative and beta to be positive, right? I'm going to make a small change. Please hang on with me, okay, right? Instead of alpha being negative and beta being positive, I think this will be a better way, okay, as the math will soon follow. So if I choose plus here, right, if my MW changes, my FW also changes, such that there is going to be a positive sign here and a negative sign here. And in this expression also, there is going to be a positive sign and a negative sign. Okay. So we call that nothing changes. The only thing I've done is the sign of the multiplicative constants I added, right, for making the equation to be dimensionally compatible, that I've just changed. Why did I change? Because it is going to be even more convenient. I thought that by having alpha to be minus and beta to be positive, it will be easy for us. But changing it is going to make our job even further easier. Okay. This is not going to change the physics in any way. I'll also recap where we are at. Where are we? we are at the stage where we have to maximize Ln W subject to the two constraints. That is, the number of molecules, the total number of molecules should be a constant, and the total energy should also be a constant. For that, we have this expression MW, right? And as part of it, I added two constants to the equation, alpha and minus beta. Okay, right? I originally included minus alpha and beta, but I realized that this is going to be the easier way. Okay, so this is the signs actually don't matter. Okay, because these are just some constants, right? Okay, so I've added alpha and beta so that this equation is dimensionally meaningful. Then I realized that my d ln W, right? My d ln W can be expressed, okay, can be expressed as sigma over I, dou ln W by dou Ni times dNi. What is the basis? The basis is that the dNi's are all independent. So therefore, any change in my ln W, right, any small change in my d ln W can be obtained as the sum of the changes corresponding to all the different Ni's. Okay, right? So that's how I could get this expression. Sorry, that's how I got this expression right here for d ln W, right? And I added that to alpha and the other terms, the alpha and beta terms, to get expression FW. But from this, I realized that, here I have three terms. In each of the three terms, if dNi were to be 0, I won't be getting any solution at all. Okay, right? However, because the RHS is 0, if the multiplicative factors, okay, right, multiplicative factors excluding dNi, if they are 0, right, then I can actually find some solutions. All right, I can actually find some solutions. Okay, so now we have this equation which has to be solved for us to obtain something. Okay, right, obtain something. What it is, I'll tell you very soon. Okay, now, so we have this expression here, right? Your dou ln W by dou Ni. Now let's consider this first term. Now here, if you consider dou ln W by dou Ni, right? Now that is given by 1 by Nj dou Nj by dou Ni. See, notice this, okay? I have, because this involves partial derivatives, right? Because this involves partial derivatives, I have carefully, used two indices here. Okay, right? I've used two indices, Nj and Ni. And when Nj equals Ni, this I'm going to call as RHS. Okay, right? Your RHS is 1. And when Nj is not equal to Ni, your RHS is 0. Why is it 0? Because the DNS are all independent. Okay, right? So your dou ln W by dou Ni can be written this way. Are we fine? Okay, right? So I use this idea. I'm now going to delete this part of the board. And so this equation right here gets modified as, right? Is going to be getting modified as Ni divided by N, okay, right, is it to be e to the power alpha minus beta EI. Notice what I've obtained, okay, right? I will give it to you as a homework, okay, because due to want of time in the tutorial, you use this particular idea that your dou ln W by dou Ni is given by this expression. And if you use two indices, okay, right? If you use two indices, when Nj equals Ni, when I equals J, your RHS becomes 1. Or not Nj equals Ni, I equals J, RHS is 1. And when I not equal to J, okay, right? When I not equal to J, yeah, RHS is 0. Why is it 0? Because the Ni's are independent. Okay, that's it. Therefore, this expression, and after this is in the form of a logarithm. Once you take the exponential form, this becomes this. Now already what have you obtained? Notice it. What is Ni? Recall that Ni is number of molecules in the ith energy state. Okay, right? And what is N? N is the total number of molecules. So you've already, kind of obtained an expression for the number of molecules in any particular given state. Are we good? Right? We of course don't know what alpha and beta are yet. Okay, right? We don't know what alpha and beta are yet. Okay, so we have this, and from this expression, I'm going to call this expression EW for exponential form of expression W. Okay, so from expression EW, I'm going to use the idea that your n is nothing but in equation EW, right? And consequently, what do I get? I get that I use this Ni over sigma over Ni, and I get that my e to the power alpha, right, is equal to 1 by sigma over I, right, e to the power minus beta ei. This is a very important relationship. What have I done? I have been able to connect alpha and beta, right? Even though I started off with two different multiplicative terms in the original expression for W, I think it was called MW, right? You may go back in the video and look at it, okay, right? I have been able to connect alpha and beta with this expression. Are we clear, right? And this means, okay, right? Now, if I substitute this over here, right? If I substitute this over here, I will naturally be getting my Ni by N, my Ni divided by N as following: e to the power minus beta ei divided by sigma over I e to the power minus beta ei. Right? This is the final expression for the Boltzmann distribution, which talks about, right, the ratio of number of molecules in any particular state, right, divided by the total number of molecules as given by this expression. Now, we now have a Boltzmann distribution. What we have not seen yet, okay, right? What we have not seen yet is that independently, okay, right? Independently. Now see, this particular term beta, okay, we have not determined what beta is, okay, right? That's a very tricky aspect, okay? That's a very tricky aspect, but you can kind of say that, okay, this is by looking at the dimensions of the BD, that is the Boltzmann distribution, you know that the LHS has no dimensions, correct? Now, what about the RHS? Now, in the RHS, of course, this is a number, so there are no dimensions overall. And EI corresponds to energy units. So, if EI corresponds to energy units, your beta, right, should also be corresponding to energy units. Okay, right? So, now, so therefore, your beta should contain some, I mean, no, I said energy units, I was wrong. It should be the reciprocal of energy units, such that, you know, it's overall a number. Okay, so I'll delete this independently. I'll come back to it in a minute. So you understand that your beta should have reciprocal of energy units. Okay, right? Now, you know, independent of this derivation, okay, right? Independent of this derivation, now, you know, it can be shown, okay, right? It can be shown, note, okay, right? It can be shown. We're not going to look at how. We shall not look how, okay, right? We shall not look how right here, okay, that beta is equal to 1 over kBt. Right? What is Kb? The Boltzmann distribution, the Boltzmann constant, which is given by R by Na, and T is of course the temperature. Now, when is temperature possible to be defined uniquely for a collection of systems? If only the system is in LTE, okay, that is like local thermal equilibrium. So, because your beta is given by kBt in your Boltzmann distribution, you simply substitute beta as 1 by kBt, right? So, this is the overall Boltzmann distribution, which tells us about the ratio of the number of molecules in any given state to the total number of molecules. And because this beta involves, you know, like 1 over kBt, right? I have not told you how it can be shown here. That is an independent statistical thermodynamics class. Okay, right? So it might not be too relevant for us to show this particular thing, beta equals 1 by kBt, right? So I'm just going to tell you that beta is 1 by kBt, although based on dimensional analysis, we understand that your kBt should have inverse of energy units. After all, this should, right? See, your kBt, if you think about it, this is R by Na, right? That is like joules per mole per Kelvin divided by, per mole, right? Times Kelvin here. This Kb is this. So the mole get cancelled out, and the Kelvin also get cancelled out. So this is 1 by joule in SI units. This is already in joules. So therefore, dimensionally, if you choose beta equals 1 over kBt, it makes sense. All right. So this is how we get what is called as the Boltzmann distribution. Herein, we use the idea of thermal equilibrium. We use the idea of local thermal equilibrium. That is, the system can be defined by one unique temperature value. All right. Now, this is the expression we used. Okay. A modified expression for BD, that is Boltzmann distribution, can also be written in terms of the degeneracies. Now see, instead of writing the Boltzmann distribution this way, one can also write Ni by N is given by Gi, where Gi is the degeneracy of the system, times e to the power minus beta Ei, where now we know your Ei is e to the power minus beta Ei divided by sigma over I e to the power minus beta Ei. Okay, right? Now just note that Ei here is not the energy of the individual state. It refers, to the collection of states having the degeneracy Gi. Okay, right? So this expression can be easily modified into this, which is what we use in our lecture. To get the Einstein coefficient, etc., etc. Okay, right? Are we clear? So what did we look into so far? We looked into how we can obtain what is called as a Boltzmann distribution, right? Under LTE conditions. That is the conditions wherein one particular temperature can be uniquely defined for a system at a macroscopic level. Okay, so with this tutorial, I've explained to you a bit about the LTE conditions and how the Boltzmann expression for the number of molecules and energy levels could be obtained. Okay, right? On that note, like I shall end this tutorial session, and I shall see you in the next class. Thank you so much.